Can begin. Full screen mode, is it? There is no full screen mode, is it? Right. Based on our previous interaction, I have slightly modified the course content. In the sense, the topics which were suggested during the interaction, I hope to include those topics. So what I plan to do is, from the next lecture onwards, or perhaps next week onwards, is to make the modified course content viewable to all. So there would be some additional topics which could be added in the first 15 lectures. Because we had to add those additional topics, there could be some deletion of minor topics which we would exclude as we go on and in the course of our lectures. In today's class, we intend to introduce our first 15 classes, first 15 lectures. In a sense, the first lecture, formation, soil type, and we'll also introduce the soil, water, air relationships, some of the important relationships which are used in soil mechanics and in geotechnical engineering. Now, almost in every lecture, every first lecture which I Is this okay? Okay. So in every lecture of mine, okay, what I like to do is to introduce on the first slide itself some unique photograph. Photograph in the sense which shows some uniqueness of our nature which exists all around us. This particular photograph was given to me by a friend of mine. In fact, we share a lot of unique features, and there is a kind of competitiveness which we try to edge one photograph which is mine is better than yours. So in order to next slide. So in order to counteract his photograph, I like to introduce one particular unique site as a part of introductory to this class, a unique site which is not far from our Bombay region. If you happen to travel from Bombay to Goa, on the way there is a station called Ratnagiri. Just 23 kilometers beyond Ratnagiri, there is a small station at Nifsar. Now, if you happen to travel to along this route a few years back, what you would have noticed was the train used to literally stop close to the station. People used to get down with the camera and literally take snapshots of the track being lifted as the train was allowed to pass through at restricted speed. So because all this happened because in 2005, when the major monsoon happened in Bombay region, a similar large track of monsoon happened in Ratnagiri as well. There was a small hillock, a small hill, which literally slid off. Okay, is it wrong? Okay. There's a small hill which literally slid from a large chunk of soil, moved below the track. What you see is, if you can barely see, is the main line and the loop line. This entire chunk of land moved, taking the main line as well as the loop line. What you see is a parabolic shape failure, and this failure went down right up to the river. That's the river. And somewhere along close to the river was a village, and the house, the flats of the house of the village also, got destroyed. Now, for the last since 2005 to 2010, various ground modification procedures were adopted. Now, we are not going to go into details of the modification, but in the sense, piles were installed, Micropiles. Micropiles, small diameter piles, very conventional to normal piles, but small diameter piles. There were curtain grouts, grouting procedures which were adopted. Uh, 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 Pipe drains were installed, and I mean the whole thing, if you look at it, since 2005, various ground modification procedures were adopted. We have a table over here which shows uh, the quantum of cement used in grouting work since 2005, that is in 2007 and 9. What you see is, if you add up the cement consumed just in over the 2-year period, it adds up to more than 50,000 bags of cement, assuming each bag is 50 kg weight. Despite all this quantum of work, what you see on the photographs on the right hand side is the village, the village which is destroyed. Okay, what you see is various sections of the well and the groundworks which were pretty much ineffective since 2000, whatever was done in 2005. Let me go to next slide. Next slide again shows few photographs of the micropiles which were installed. The whole soil, rather than the soil behaving as an arching behind the micropile, the soil simply moved downhill, destroying the pile beam. Or the other photograph shows cracks on the village walls. Similarly, the whole pile system being collapsed. If you look at all this, an expert report was made on this issue, and a very, I would say, humorous statement came out of this report was, it's a nature's theory. Does it mean act of God? Okay, this is, which you'll find it amusing. But as an engineer, you will notice that all this, the soil behavior, is happened because of if you look at the sketch which is drawn on the right hand side, it's a cartoon which shows an idealized rotational failure. That's a slope failure. Okay, and the various parts of the slope failure. Let's follow a few parts. That's our transverse cracks. Similar transverse cracks were observed down the hill, down the slope, which were photographed over here, as you see the photograph at the bottommost photograph. The slump which was found at the bottom of this failure is very similar to the slump which is shown in the idealized idealized cartoon. There are back slopes which were quite visible by the tilting of the trees on the other side. Likewise, what we say is this whole failure was a typical slope failure, which for 5 years I would say we failed to notice that rather than a slope failure, we used to think whether there are cavities below the ground. So this leads to a very interesting topic which I'd like to begin or introduce today, is the unique nature of the soil. So that's our talk for today. We often say that soil deposits are unique. Unique because they have been deposited under a variety of variable conditions which have been placed by the nature. So let's take an example. If you take soil samples from two adjacent points not far from each other, you will find that the soil samples could show a wide variety or wide variation in the property. There can be also unexpected changes which can occur even when you have the soil from the same site. Take an example of, you have sand sample which you have simply vibrated from a loose state to dense state. You will see that the mechanical behavior of this sample changes by tremendous magnitude. Take another example of, clays which are, extremely hard when they are dry, but when the water content changes, they become slush, or the strength, there's a drastic reduction in strength. I'd like to take an example of the last two lines is by quoting sensitive clays. In fact, clays which are sensitive have very high, I would say, a fair amount of shear strength or strength when they are not disturbed, but a slight disturbance will cause the strength to decrease by a large magnitude. Now over here, it's a good idea to introduce you to a small video, which I happened to see last night. I looked at it at YouTube. It's there. Can we look at the video? I forgot. We should have uploaded it before. I don't remember the link. Just if you can show internet on the side, and I'll just. This is not active, right? Yeah. Hello, no video, no audio, no. Please close the video wall so that colleges can see teacher video. I think they don't want to see this. They just want to see this video. Okay. Right. We're not going to totally run this video today. What I intend to do is to, if you do a simple Google search, internet search on RISA, R-I-S-S-A, RISA slide in 1978, you'll come across this video, a 20-minute video, which shows how quick clays, the behavior of quick clays is very strange. Quick clays are the sensitive clays which we just spoke about. In fact, this video, few years back, I had purchased this video from NGI. They used to sell this video for about 7,000 rupees or so. But I was quite surprised to see yesterday that this video is now freely available on YouTube. Please do search, do click search on RISA, R-I-S-S-A, RISA landslide. You'll come across this video, which is quite interesting. Okay, I'm going to stop this and come back to my lecture. Okay, now let's move to the next slide, please. So when we deal with natural deposits such as soil and rock, we say they are complex. A certain why the question is why. I've listed on 5 points, which of course are not exhaustive. There could be a number of more points. The very first one is the stress-strain relationship for soil deposits is non-linear. Now this is amongst all the materials which we use for construction or for our day-to-day usage, soil is the most unique material because of the first step, that stress-strain behavior is non-linear. Right from if you plot the stress-strain plot, right from the origin, for many soils, the curve starts to show as a non-linear behavior. Now, if you are able to predict this curve, the stress-strain curve for a soil, in fact, for any material, I would say our job as an engineer is finished. That's our job, at how to get this curve right. Okay. The second thing is soils have memory. I always like to quote that soils have memory of an elephant. For example, if you load a soil to a certain value, a certain magnitude, and as long as you don't exceed the magnitude, the soil will always remember. It's like an elephant. If you hit the elephant once, even 20 years from now, it will always remember you that you hit the elephant. Same thing goes for the soils. The third point. Soil deposits are non-homogeneous. We've just seen that from one location to another, soil varies. The fourth one is important. When we do laboratory tests on samples or field tests, in fact, we only test a small quantum of soil compared to the soil which exists at the site, which may be tremendous, which bears the load. So the tests which are carried out are only on small samples, only on small quantum. Lastly, we say we collect samples which undisturbed samples, and to be true in nature, no sample is truly undisturbed. despite saying that, we are not able to capture the joints, fissures, weak layers in the soil, which you will not be able to capture when you extract small chunks of soil sample from the ground for laboratory test. This leads to the our interesting topic is how the soils are formed and what are the different type of soils. Okay. In fact, this snap over here on the right hand side is taken from the same video which the link which I had provided. I hope you will enjoy this video. Coming back to this slide, the soils which we say are formed, or there are three, or I would say there are three kind of origin. The soils are originated from three different components. The first group is whether the origin is from physical or mechanical weathering, okay, of the parent rock. We always speak about weathering of the parent rock. So if you have a physical mechanical weathering, that's the first one. Compared to the chemical weathering of the parent rock, that would be the second origin. And the third one is the organic. We'll speak about these three in detail on the next slide. So these three are physical, that's the mechanical. So when we say mechanical weathering, it just includes as if you have a sledgehammer and you have broken down the rock piece into the smaller components. When we say sledgehammer, nature has its own sledgehammer, in the sense the flowing water, the weathering nature because of the flowing water or the wind or ice in fact. Okay, all this creates an impact on the bigger chunk of rock, and the grinding effect makes it into a smaller pieces. These smaller pieces retain the original mineral component or the mineralogy of the parent rock. Take an example that the sands and gravel and coarse silt to some extent are the examples of the physical weathering of rock. The second one is if the origin from chemical weathering. The chemical weathering can be because of oxidation, hydration, or even leachate. When leachate of certain organic or inorganic acids into the ground through the rock, and they create a new set of chemically weathered rock. These chemically weathered or chemically decomposed rocks are in general fine grained. When we speak about fine grain, we'll come to this term later again. Fine grained are your anything which you need a hand lens or a finer than hand lens to view them. Examples are clays and fine silts to some extent. The third one is if the origin is of organic in nature. Now, the organic in nature, they are usually, if you look at them, they are very fibrous. In fact, a good example is peaty soil. Fortunately, in this part of the world, our peaty soils are not very largely spread, and we often do not come across these deposits. But if you happen to travel to some European countries, peaty soils is a big problem over there, where the fibrous nature of the soil makes it highly compressive material. You can take an example of peaty soil if you happen to visit the nursery where they grow plants. You'll find that if you can ask peat from them. They will be happy to provide this peaty soil at something like 30 or 40 rupees a kg. Okay. Next slide. When we speak about the origin because of the physical or mechanical weathering or the chemical weathering, now these two origin can also be sub-classified, or I would say called as either residual soil. So I would say residual soil can be a subdivision of physical chemical weathering, and the second one is transported soil. Both these terms, as the name sounds, it means as residual soil would mean the soils which are at the same origin, at the same place as they had originated. And as the name sounds, transported soil would mean soils which have been transported from one end to the other because of the forces of nature. Take an example of water, wind, and even ice. Okay. Because of these transported agencies, you'll find that there is particle segregation. Take an example of the river Ganga, right from where the flow is quite large. You'll find only the heavy particles settle down first, and as the river Ganga originates towards or I must say ends towards the Bay of Bengal, you only see fine silts and clays where the finer particles are able to stay. So there is some good amount of segregation as the river flows. Okay, this they also affect the shape and roundness of the particle, the the transported soils. Sorry, I think I double clicked. Yes. Sorry, let me go to the next slide, please. On the next slide, there are examples of transported soil, and as the name sounds, if you scroll down this figure, this slide, you'll find as the name sounds, the level of transporting agencies are the ones which cause the name, or which have the name in the name of the soil. So take an example, the first one, alluvial. Alluvial soil is because of a river. Alluvial, we know, is because of the running water in the river. So any deposits which are formed from suspension in running water. Second one, lacustrine. Lacustrine is fresh water, lake. So you have lake deposits. Marine, as the name sounds, marine seawater deposits which are from suspension of seawater. Aeroline, again as the name sounds, air. You have deposits which are formed because of the air transported by the wind. Lastly, glacial. Glacial you'll find, when we speak about glacial deposits, you'll find both larger chunks, smaller chunks, fine sands, going down to silts and clays. There's randomness or heterogeneity in the deposits because as the particles get crushed, as the glacier starts to move down the slope, the particles start to get crushed. There are some generic names, and because we were onto this topic, I thought of introducing a few generic names as well, and we'll quickly go through the names and we'll quickly go through the names. The first one being Lewis. Lewis are the weakly cemented. When you say weakly cemented, the cementitious property is because of the calcium carbonate. So any soils which contain calcium carbonate will cause weak cementation, which makes a soil more friable. In fact, there is also a clay content called Montmorillonite. Now we'll introduce this Montmorillonite later, but it's a very a swelling clay, and it has, I would say, a major part of our country has a large chunk of Montmorillonite clay, and it's formed in semi-arid or arid regions. That's Lewis for us. The second one is a tuff. Tuff is again has some cementation, and the origin is because of the volcanic. The third one is bentonite. Bentonite is again, some people like to call it bentonite or smectite. It has the clay mineral component, is the same clay mineral component as the Montmorillonite. That is the clay mineral component in bentonite. We'll do this later. We'll of course cover this later. Glacial till, we've just looked at glacial till. It's a mixture, it's a heterogeneous mixture. So we'll skip this, we've just looked at it. Warped clay is the next one. Before I continue, let me see if this file is downloadable. You can download this file. Okay, apologize. I have permitted download of the file. So on your PC, you can right click and download the file. You need not jot down each and everything right now. you may jot down something which I speak or something which is not visible, written on the slide, but anything which is written on the slide, you're free to download. Please let me know if you have any difficulty. I would not like you to copy all this because we don't have time to allow the slide to be available for substantial amount of time for you to copy. You'll just go through the slide and you can review the slides at home at leisure. Okay, please let us come back to the next one. Warped clay. Warped clay is alternate layers of, a fine grain deposit and a coarse grain deposit. So I would say if you have clay deposit in cold weather, so during small runoff, meaning when the rains, there are no rains or the rains are less, you have fine deposits coming up, and silts and fine sands to some extent coming up when there is heavy runoff or the rainfall is large. Marl is again weakly cemented calcium carbonated of marine origin. Gumbo is another soil which is highly plastic, dark colored clay. The next three, which is peat, muck and humus, if you happen to touch any one of these soils, they are easy to identify because of the smell. The smell because of the organic matter present in them. The peat, we have just discussed peat, it is fibrous and highly compressible. We would like to avoid the use of these soils for as a foundation soil or doing as a construction material. Muck is usually found in swamps. It's mixture of fine particles of inorganic soils and decomposed matter. Humus is very similar. Dark color consists of organic matter and also mixture of topsoil. In fact, humus is something which we use for our as a fertilizer, a natural fertilizer for our plants. A hard pan is an extremely hard, extremely difficult to do through cohesive soil. If you have, you'll find a lot of these deposits in the northern regions of our country, the hard pan, and it's difficult to drill, and most of these deposits are highly compressed. So there is, despite being clay, you will find that the compressibility of these soils is extremely low. Next slide. You have collovial soil, which is, as the name defines, it's a rock debris or at the bottom of a steep cliff. So in fact, collovial soil would be your residual soil. A mine tailing is a transported soil because you have it's been deposited. Usually mine tailings are deposited by hydraulic fill. When you say a hydraulic fill, meaning it's like using a hose pipe and allowing the soil slurry to be deposited using a hose pipe. Try to visualize this. If I use a hose pipe and through the pipe a soil slurry comes out, you'll notice that the heavier particles will settle down first and the lighter particles are transported or settle down much further away from the mouth of the pipe. Same thing happens for mine tailing. You have segregation of particles as the soils are deposited. The fill ground is any ground which has been which is well compacted. So when we speak about fill, it always means that the good engineering methods have been used to compact the soil. So the rollers have been used, or some kind of impact load has been used to compact the soil. That is fill ground for us. So some engineering has been used to compact the soil. Alternate to fill ground is a made ground. This is a term which is quite, normally you'll find this term in many geotechnical investigation reports, wherein the near surface soil, if they have good amount of waste, meaning any rubbish material, whether it's your tiles, your brick bats, or other construction rubble, or even your bathroom sink, parts of sink, so anything which is non-engineered and is simply dumped is your made ground. Okay, we come to our the important topic for today. Okay, this is the important topic, and I would like you to please look at or listen very carefully. If you're half asleep by now, please wake up, because the set of equations which we will cover in the next 15-20 minutes are really important for us, and they will lay the foundation for our not only next 40 lectures, but even the lectures thereafter, which would be covered in your routine classes, and even when you go out for and practice as an engineer. These relationships are normally in standard textbooks. They are called as soil, water, air relationships, and these relationships are because of we say when we speak about soil, we say that the soil is usually a three-phase system or a medium. Please look at the cartoon which has been drawn. The ones which are shown by red and have center X written over are your random soil particles. In between the soil particles, you will find that there are empty spaces. There would be empty spaces because these are all random in shape. Some of the empty spaces are filled with water, and they have been written, marked as W. The other empty spaces have been highlighted by yellow, and they have been written as A. That's air for us. So you have a soil mass which is a three-phase system, which has solids, and within the solids it has gaps. We look at these gaps, the term is called pore. We will look at pore space in a while, and the gaps are filled either with water or with solids. Now I would like to really look at this figure in the next slide. So I'm looking at this figure again in detail. In this figure I have removed the soil particles, the red color soil particles outside, which is on the left hand side of your screen. The solid they comprise of grains of minerals, or the origin can be of organic. They can have organic origin. The other, the gaps which we discussed, which were the air and the water, I have removed it towards your right hand side of your screen. The right hand side of the screen are again the air gaps and the water gaps. These air gaps, which is the gaseous matter, and the water, which is liquid, they occupy the space, the open space, which is termed as voids. Now I would like to make a statement over here. Most of the terms which we use in our engineering practice, as an engineer, are the terms which we use on day to day. So the voids is common English, gaps, empty space. So this is the term which we use, in which the gaseous matter and the liquid is filled up. The liquid phase, okay, generally it will be water, unless we are dealing with contaminated soil, but generally for I would say 80 or 90% of practicing engineers, it is normal water. The water would partially or wholly fill the voids. If they partially fill the voids, the remaining part of the voids would be the gas. The gas is usually air. Again, we speak about air because we don't want to bring in the contaminated soil into picture. So it's usually air and water. Let me go to the next slide, which will really speak much about it. It says the proportion of the solids, the water and air, which is present in the mass, soil mass, does influence its physical. When we say physical, it means mechanical behavior of the soil. And you will look at these three components, the relationships of these three components in the next 15 minutes. Usually the three components are stacked on one top of each other. So what you see is a Lego. The bottommost Lego or the block is usually the solid, or represented by S. On top of S we have the water. The block or the Lego represented by water, and the topmost block or the Lego is the air. Remember that this figure is not drawn to scale. It does not represent any scale. But what it represents is, by convention, the left hand side is always represented as volume. So if we speak about volume on the left hand side, the bottommost was the solid or our soil particles. We represent this by volume of solids. That's your volume of solids. And remember, this is not drawn to scale, I repeat. Some textbooks or some people like to call this solids as skeleton. So that's the soil skeleton for us. The next two, if you recall, the second Lego and the third Lego, the top two represent our voids. So in combination, this should be your volume of voids. That's VV. Volume of voids consists of water. So the second one is volume of water, and the topmost one is volume of air. So to summarize, the total volume, capital V, is represented by Vs, volume of solids, and volume of voids, which is the top two Legos. This was the left hand side of the blocks. The right hand side of the blocks represents the weight or the mass. So in this figure, we have the weight. The bottommost represents the weight of solid. Remember, this is not to scale. There is no scale used. But the weight of solids is the bottommost. Compare this to the top one. The air will not have any weight. So weight of air is 0. And it is only the weight of water which occupies the voids. The total weight is written as capital W, which is again, like I said, the weights are on the right hand side. The two extremes to this three-phase diagram. So we have three phase, 1, 2, 3. There will be two extremes to this three-phase diagram. The bottom two figures show the two extremes. If you look at the bottom left figure, the bottom left figure speaks about a saturated soil. Now we will come to a saturated term called saturated in the next 2 or 3 slides. But for the time being, let's visualize that all the air pockets or the air voids have been filled with water. So you now have water which is over there. That's just one extreme end. So in other words, the volume of voids only includes volume of water. Similarly, the other extreme on the right hand side would be when the soil is completely dry. So there is no water. So in other words, all your voids are now empty, air, only air, there is only air. So we have volume of voids same as volume of air. Okay, that is the other extreme. Can we pause and see whether if anyone has a question? We'll just pause and look whether there is any comment till now. No audio. Who's talking to them? Here? This one. Okay, before we continue, do we have any questions, please? If you have any questions, please select hand raise on your screen. This chat box, we are not looking into. Yes. Good morning. Can you hear me, please? This is IIT DHU.
Good morning, sir.
Good morning.
Hello, sir. Good morning.
Yes, we can hear you. Good morning.
Pardon, sir? From my one boy. So good morning, sir. Hello.
Good morning.
So you mentioned about the generic names of the soil, sir. So what are exactly these, sir? Why are we using this? What is this convention or something, or we use on the field?
Okay. Uh, I would say that's a good question. In fact, I would say that's a good question. Even it has made me think. Many a times, when you go out as a practicing engineer, uh, you would like to, put in names. In fact, when you say generic names, there could be another class of generic names which are more of localized names where the local people like to call them. For example, the first name which we had, the Lewis, if you recall, the Lewis was the first one, deeply cemented, soils. Usually, the Western people, when they want to discuss the soil, the normal soils to general engineers or the general public, they would not like to call them as sand, cemented sand, or silts. They give some kind of names through which you can at least easily communicate some few properties of the soil. So these properties, when you say Lewis, take an example of Lewis again, it immediately comes to our mind that if I break the soil lump into individual particle, they will not come back and combine again because the cementing properties are gone. So as long as the soils are undisturbed, they are weakly cemented. So that is the by mere mention of one name, it gives you the complete scenario or the picture of the soil. So I would say it's a better way of describing the describing the soil rather than me putting weakly cemented sands or weakly cemented silts to some extent. I hope I was able to answer your question. The echo was not from outside, right? Well, okay. Good morning, GCT teacher.
Good morning. Good morning, sir. I have one doubt of warp clay. I told that warp clay is a function of 50 mixtures and montmorillonite. Can you tell me about montmorillonite, which is a good mineral in clay? Can you tell about warp clay?
Okay, warped clay is morillinite clay. Warped clay was layered deposits, where you have usually heavy rainfall during the monsoon period and little water flows through the non-monsoon period. That is warped clay. Are you able to hear me?
Yes,
Whereas
sir.
Montmorillonite clay we will deal with Montmorillonite clay mineral later when we speak about mineralogy, uh, clay mineralogy. But it is a highly plastic clay. That is, to begin with, it's the most, it's the worst clay it's like, we say it's an engineer's nightmare. Okay? Okay, coming back to you, please. Yes. Yes, GCT teacher.
Another one doubt is sir, another one doubt is
Yes, please.
here not audible, sir.
Audio is not good.
Okay. Sir, another one doubt is soil origin. One of the soil parameter is tough, sir. Can you tell me about the tough?
I think if you intend to go look into detail about this, again tough is again cemented. So it's another class of soils which is again cemented. Further details, I think you can probably go and search for standard textbooks, but it would not be possible to give too much details about individual generic names. Okay. There is no audio coming from your end. Any other
Okay, sir.
question?
Thank you, sir.
Thank you.
No, sir. No, sir.
Yes, KNMU teachers, we are with you.
Hello, sir. Sir, my question is, you have shown the chart that air, water, and solid chart, okay? You have also mentioned their voids. So, what is the difference between the air and voids in the chart?
No, if you have a dry soil, there is no difference between air and voids, because all the gaps, all the voids are filled with air. Whereas if you have a partially, your voice is echoing. If you have a partially saturated soil, soils which are have air as well as water, then there is a difference, because your all the empty space, all the voids are not filled with air. So there is a huge difference that for partially saturated or soils which have some water and some air, definitely air and voids are not the same.
Not getting. Sir, will you say more again, sir? I didn't get that difference, sir. Voids and air.
Yeah, okay. We'll look at some expressions, and then maybe it will be more clear. I think as we move along, it will be more clear in next 10 minutes.
Okay. Thank you.
Okay, so can we go to this full screen mode is? No, full screen. That's better. If you make it small screen, you can see this as well. I think this is better then, at least. Okay, we have about 10 minutes, and probably we'll go through the remaining part of this lecture. What we see is a three-phase. We spoke about the three-phase, and we just have finished speaking about that the volume, that is the total volume, should include volume of solids plus volume of voids, and the volume of voids was volume of water plus volume of air. In case you are slightly confused over this, we will go to the next few slides when we look at the individual term in detail. Let's look at the first one, which is water content. Please ignore the figure on the right. We'll just look at the water content term. And for the next few terms, I would like you to take these as a tablet. A tablet meaning you just them. That's how I like to say. Take them as a tablet. So the first one is water content. Water content is also called as moisture content. It's the ratio. The ratio would mean that there is no percent. As I write 100 multiplied by 100, it becomes percent. If the 100 does not exist, it becomes a ratio. So it's a ratio of weight of water or the mass of water to the weight of solids or the mass of solids. I'm not sure if the figure is very clear on your screen, but it is weight of water divided by weight of solids. This is water content. Just a second. The same thing has happened over there. This is water content for us. Usually the water content is less than 100% for many soils. Take silts and sands to some extent. The sands may have a water content at site in situ of about maybe 10-12%, a maximum of 17%. Usually 8% or 7% is quite common. Clays have much higher water content. They can have water content of about 20% and higher, or even up to natural clays can have water content of 30%. But usually this is less than 100% as read on your screen. A water content of 500 up to 500% is possible for clays which you spoke about, which contain Montmorillonite clay. If you happen to be an undergraduate student and if you are able to remember this term Montmorillonite clay, I would say hats off to you. So I salute to you, because as an undergraduate student, this is one of the tricky words to remember. Okay. Go to the next slide. Sorry. Okay, the next term is void ratio. Again, I would like you to take this as a tablet. Void ratio is represented by E, small e. I'm not sure, let me see if it's clear on your screen. That small e is the ratio. It's always expressed as ratio, never percent. It's the ratio of volume of voids to the volume of solids. If you look at this carefully, both the numerator and denominator are independent. Okay, let me zoom out, please. Let me zoom out. Zoom out. I think, yeah. Let me handle this. Or if I make it full screen, does it become full screen for them? Right now, it's like this for them. So the void ratio, apologize, let me come back. The void ratio is a term usually like I said, both numerator and denominator are independent. In other words, this ratio can be more than 1. For clays, you'll find a value of void ratio above 1. It is possible. For sands, usually this ratio is about 0.7, 0.6. So the typical range of values have been given on your screen. We will introduce one more term which is called a specific volume. It's represented by small v, and specific volume in fact represents the total volume of the soil. Okay, so when I say specific volume, small v, I'd like you to look at the bottommost equation. Okay, I'll just zoom in. The bottommost equation is small v specific volume equals 1 plus void ratio. Let me go to next slide, please. The next one is a porosity. Porosity is again expressed as percent. So it can be a ratio or it can be as a percent. Porosity is defined as volume of voids to the total volume of the soil. If you look at this very carefully, volume of voids is dependent of total volume. So it is like a sub-matrix of total volume. If I want to rephrase this, the numerator is dependent on the denominator. In other words, this ratio or this percent can never be 100%. That is why porosity, the range is between 0 and 100. It can be shown, and we will discuss this later, is the is the relationship between porosity and void ratio, which is porosity equals void ratio divided by 1 plus void ratio. Likewise, you can play around with the terms and then express void ratio equals to porosity divided by 1 minus n. This leads to the next term, which is degree of saturation. Degree of saturation is defined as volume of voids to the degree of saturation is defined as volume of water to the volume of voids. If you look at this term very carefully, the numerator is dependent on the denominator, because volume of water will always be less than the volume of voids. In other words, this ratio will not exceed 1. Or if I want to write this in terms of percent, this percentage will not exceed 100%. If I want to rephrase this, if I say my degree of saturation is 100%, I will say my soil is saturated. Okay? It cannot take any more water. That is my saturated soil. The next term is air content. The air content is defined as 1 minus degree of saturation, 1 minus S. Over here, S represents your degree of saturation. So air content is AC equals 1 minus degree of saturation. Let me zoom in, please. Zoom out. The next thing is percentage air voids. Percentage air voids equals to volume of air divided by total volume. And if I multiply by 100, it becomes percentage air void. Usually this term is not well used in our engineering practice. At the most, you will be more comfortable with usage of air content. But then nonetheless, it's a good idea to know what percentage air voids is. What equals volume of air divided by total volume, and if I multiply by 100, it becomes percent. Let me go to the next slide, please. Before I conclude today's class, I'd like to spend the next 2 minutes on something which is we as engineers are quite we mix them up, and believe me, even our colleagues, even myself, we mix this up in our day-to-day practice. Is a term called density. Should we use the term density or unit weight? You'll find that the density in our school we have been taught density is mass per unit volume. And on the other hand, when we speak about unit weight is represented by gamma. Gamma is weight per unit volume. Density is represented by rho, unit weight by gamma. Density, units of density, SI in SI system. Remember, we always like to follow SI system. The units of density are in kg per meter cube. That's normally we will use, or sometimes megagram per cubic meter. Megagram is capital mg. So capital mg is megagram per meter cube. Okay, please be careful about this. In many soil report and many engineering practice in this part of the world, we use grams per centimeter cube for density. Remember, grams per centimeter cube is not SI unit. So if you have to follow SI unit, you normally would like to follow kilogram per meter cube or megagram per meter cube. So it's a quite easy, the conversion is quite easy. 1 grams per centimeter cube equals 1 megagram per meter cube. If this is clear, let's look at the unit weight. In the next slide, the unit weight is remember, was represented by gamma, and the unit weight is usually, the units weight is written in terms of kilonewton per meter cube. Okay, that's kilonewton per meter cube for unit weight. If you have to obtain unit weight from density, the easy conversion is you multiply density times the acceleration due to gravity, which is g, and the value of g is 9.81. So if you multiply 9.81 to density, you get unit weight. Okay, to simply put it, in our lectures or in practice, when we use density, we will never use kilonewton per meter cube. I would say this is a rather incorrect way of usage. Density should always be associated with grams per centimeter cube if I am happy with CGS unit, or megagram per meter cube, and kilogram per meter cube if I am happy with SI unit. And if I want to use unit weight, I will only use SI unit of kilonewton per meter cube. Incidentally, this whole thing, if you happen to look at some of the ASTM codes of practice, okay, please do a Google search on ASTM. You'll find a substantial amount of literature available. It recommends that you should use density. Okay, you should use density. That means grams per, density in terms of SI unit are megagram per meter cube or kilogram per meter cube when you want to represent your mass per unit volume. Okay. So I would like to stop over here. We have crossed our 1 hour period. If you have any questions, we can have 1 or 2 quick questions, please, before we end. But who's the ZAUT? Okay. We have a question from KNMU teacher. Please. Teacher. Please.
Hello. Good morning, sir.
Good morning.
Hello. Sir, my question is, what is the difference between saturated soil and submerged soil?
Okay. We will come to this. I think that was, we will still come to this, but since you have raised this question, let me answer this. You know, a saturated soil is a soil which has all its voids filled with water. That's saturated for us. A submerged soil will also have its void filled with water. So that way it is the same. But the only difference is submerged soil will be under water table. There should be a water table for submerged soil. And usually, you know, if you happen to look at a term called buoyant unit weight, you know, the buoyancy term, that is associated with submerged soil. So let me rephrase it. I can have a lump of soil which is saturated, but it is not submerged. But if I take the same lump of soil and go within the swimming pool, that becomes a submerged soil. So submerged soil is more important when we speak about, you know, the mechanical behavior of the soil, when we want to speak about how the strength of the soil will look like. That becomes different. So the difference actually is more prominent when we speak about mechanical behavior, but nonetheless, coming back to the difference, a submerged soil would be under water table and a saturated soil would also be, the same voids are filled with water, but it is not under water table.
What is the percentage of water in both of them?
Sorry, can you repeat your question?
Hello sir, my question is what is the difference between the percentage of both of the soil?
What is
Percentage
the
content
difference
of water.
between?
What is the difference between the both of the soil in water content?
The water content will be the same.
In both the soil?
Yes. Yes. For submerged as well as saturated soil, the water content will be the same.
Okay. Oh, thank you. Okay, thank you sir.
You're welcome. Yes, IIT BHU here with you.
Hello. Morning, sir.
Good morning.
Sir, my question is regarding the formula that you gave about moisture content. I want to seek a clarification. Is that by when using that formula, is it are you using mass or are you using weight? Because if I am not wrong, in a country like India, where elevations vary from 0 meters near the coastal regions to up to 4,000 to 5,000 meters in the Himalayan regions, especially in Kashmir, where construction goes on. So if you're using the formula, if you use weight in that formula, then the value of G changes not considerably, but when you use that formula in moisture content, the content of moisture will vary according to the height because G will vary. So will the moisture content vary or not? Because if you're using mass, then the same moisture content will be there for any region.
Okay. Whether you're in India or any part of the world, for a practicing engineer, the G value is taken to be constant. If you change the G value, you would normally take a practicing engineer, you would take it as 9.801. That is the thing. So whether you want to go to Himalayas or you want to do a test somewhere along the coast, I would still say we would not change the G value. Although your question is relevant, but for practicing, it is, I would say, it doesn't make any difference to the answer. Let me just continue with this. Water content is usually expressed up to 1 decimal place. So if I want to express water content, say 17.109, it is still 17.1. If you change a G, if you want to change water content based on G value, you will not find any difference. In fact, some of the codes, if I follow some of the AS codes, they recommend that water content should be expressed as whole numbers. So in other words, I should be writing 17% and not 17.1. So to take that example further, it would not matter if you take G value as 9.8 or 9.8. Some of our students, they take it as 10 and the answer is still correct because you're not really, varying the number by a significant value. Okay?
Thank you, sir. Thank you, sir. That'll be all.
You're welcome. You're welcome. Yes, GISCE teacher, we are with you.
Sir, my question is, we not use percentage error voids as engineering purpose. Why?
Can you please repeat your question?
did not use percentage error white as engineering purpose. Why? Formula is VA equal to VA by V into 100. But this is not used as engineering purpose. Why?
Okay. See, as we will see in our lecture 2, many of the relationships which can be derived, or in many, I would say many texts derive the relationships by not using this percentage error voids, because you can do it. It does not mean that you cannot derive the relationships. Uh, Even you can also derive the relationships using percentage error voids. You can still do that, but it is like, you know, if I like saying, if I can solve this by remembering just 2 equations, or if I can solve this by remembering 4 equations, which is much better? A solution by 2 equations seems to be much better. That is why all the relationships which we will see later, you will find that they can be derived without you know, a usage of percentage error voids. I believe that could be the reason that it is not commonly used in engineering practice.
Thank you, sir.
You're welcome. Any more questions, please? You can still take one more. Chat someone. JISE is us. Okay. So no more questions. We will conclude today's class. Thank you.